So, very good morning, one and all. We are learning the subject of electromagnetics or electromagnetic field theory. So, we will learn here the topic of your the waveguides. We have seen the basics of your the waveguides. We have studied as well as the learned about the application of your the waveguides. We have also observed, studied in the previous lecture about the waveguide, how it will be affected, what are the frequency ranges, what will be the effect of wave propagation if we are considering the waveguides in the transmission line and the microwaves and all, which is the best suited as per our the application. Even we have gone through the many equations, many figures, many diagrams related to the waveguides. Even we have seen the classification of your the waveguides, that is a rectangular, circular and all. So today we will continue the one of the type, that is nothing but your the circular waveguides. Okay, even we have studied about the modes of your the waveguides, how it will be work, how the propagation will happen, in which particular mode, how we can calculate our the wavelength, what will be the effect of your the frequency, how we can calculate the cutoff frequency, how the various modes are available, and depending upon the application, how we can place all these things we have seen. Okay, so today also we will try to complete the theoretical part related to the circular waveguide. So if you're talking about the circular waveguide, definitely the name itself indicating that is looking like a cylindrical or the cylinder or the circular form. Okay, so this waveguide will be the homogeneously filled, means in that the material will be there, and the effect of your the electricity you can observe in terms of the electric as well as the magnetic field. So these if you are going to consider such shape, that the such type, that is nothing but the circular, definitely they will be independent of your the electric as well as the magnetic transverse fields. Okay, so here what will be the case, even though we are considering, if just take the example, if I am going for the mode of your the TM, that is nothing but the transverse magnetic modes. So if I am talking about the transverse magnetic mode, that is denoted by your the TM. So definitely if you observe the cylinder in unit number 1, already we have studied, if cylindrical part is there, how they that you can cut it, and how the radius you can find, and how you can find the inner radius and the outer. So cylindrical, you know very well, rho phi z will be the coordinates of that. That is also possible. So here what they are taking here in the circular manner, we are interested in the relative permeability. Okay, so this will be the area of surface, and z will be in the z direction, you can say. So in this way, rho phi z will be the three coordinates in the cylindrical coordinate system. Psi will be your the fluxes or the charges, which will be, because one of the law, that is nothing but the Gaussian, psi is equals to q. Okay, that is nothing but the charge will be equals to number of fluxes. So here, why I have taken here the vector, just because of in the is direction. So in this way you can calculate the rest of the part which is related to the what we can say, the circular or the cylindrical type of your the um, in any either in the transmission line, in the microwaves, or in the waveguides here. So here we are interested in the psi, that is nothing but the flux linking, and here is nothing but the J is nothing but the current densities form. Okay, if you are taking the JS, JV, so that will be the what we can say in terms of the volume on the surface current density, or the volume current density, like this you can find easily. So these are the constant term, that is nothing but the Kp. Rho is nothing but the radius. Here in many of the textbook they can refer as a radius, or they may write the radius as a r also. So in this way you can find the things. Here with the K is nothing but the total constant point, and with the help of the radius constant as well as the particular direction, you can find that equation. How we can elaborate how uniqueness you can find it. In the Ampere circuit law, in the uniqueness law, you can find easily that, okay, how I can find my parameters, that is nothing but the rho phi z. Okay, how they are uniqueness, or how the what are the common things, or the how we can find the solution from that. If I am changing my the value of the rho, if I am changing my the value of the phi. Okay, likewise, because the z is in the one particular direction, no issue for that, but the phi, that is from the 0 to 2 pi, how that is changing from the 0 to so and so up to the 2 pi, that will be the case. Okay, and similarly the rho, how the radius will be changed every time. Okay, from the, if I am taking from the 0 to 2 pi, from 0 to 2 pi. Likewise, so this side, that is a flux linking, there will be the variation of your the flux from the 0 to up to the 2 pi. If you observe the sinusoidal waveform, you will be able to find from the 0 to pi, pi to 2 pi. At every instant we can find easily the my phi. If my phi will change, then definitely my entire equation will be the change. Okay, so in this way you can find easily what are the variation in the phi. You can substitute that value of your the phi, even what will be the effect of the radius on that, that is nothing but the rho, that also you can able to find. And one thing is clear, that is in the z direction. So only what is the change, radius will be the change and the phi will be the change. But at present I am observing for the variation in the phi only, that is changing from the 0 to 2 pi. Z will be as it is, rho will be as it is. Okay, so in this way you can find the n number of unique units. You can find the solution with the help of this variation in the 5. Okay, so even n is nothing but the number of nodes, you can say, because the mode is changing. M and n, we know very well. Yesterday on in the previous lectures we have studied about the either the TE or the TM, that apostrophes of M comma N. So definitely M and the N are the different, and depending upon the mode of operation there will be change, so that we need to keep in our mind. So in this way, how we got this expression? This expression can be get in which particular mode they are, how they are traveling, how that cylinder or in the circular form, how the wave will be propagating that, in which particular direction, how they are changing, how what will be the effect of your the angle, how they are changing the exponentially, that is a cos and the sine form, which are the constant parameter. With the help of that we can find all these things. So that will be the expression for related to the circular waveguide. Similar to that, if the field should be the finite on the z axis, obviously if I am talking about in the z direction, that should be the finite instead of infinite. I must know the length of that in the z direction, then only it is possible to write out the find out the differential length, that is nothing but the dl in the z direction, that is a dz again. Okay, so in this way we can calculate, as I am saying, this is my side, that is a flux linking. So here I am considering as my radius is the 0 and the phi will be as it is and z will be as it is. Once will be changed, if this radius will be changed, definitely that will be changed for everywhere. Okay, so in this way I can write my expression in that is in the flux linking. Okay, if I whether my phi is varying or not, whether my rho, if my rho, if I am going to substitute here by considering this the expression, that is my rho is 0 here. So at this particular his rho, so entire term will be treated as here the 0. So e raised to the power will be this constant term will be as it is. Now third is nothing but, third case is nothing but, this is one of the sentence equation there. Okay, so that is Ez in the form of Ez. Why we are taking here the A at the place of the rho, that is a radius, we are taking that the radius is in the form of a small a. Okay, but in the z direction. So electric field intensity, okay, we are interested in the TE, you can say, mode, and that to z direction. So and my radius is nothing but, rho is nothing but my a, and the phi will be changing every time in the z direction. So how I can write my expression, that one's in the form of your the z direction. So this is the one of the way we can write our expression depending upon entire term whatever we have studied. So that is possible. How I can write my the imaginary part, how I can keep my constant term, how I can get my dou by dou z square, all this thing. This will become even in the gradients also, because in the units we have studied how the dou term will come, how the gradient come, how the squaring of the dou square by, if I am taking my vectors, so dou by dou x, dou by dou y, dou by dou z, likewise in the x, a, y, z direction. And if they are in the cylindrical, so definitely that will be the dou by dou rho, dou by dou phi, dou by dou z. Already we have done in the unit number 1. In the spherical also the r theta phi. So this will be expression will be changed every time if this is the Cartesian. That's why we are taken as in the Cartesian. But here it's not the case of the Cartesian. Here is the case of the third parameter, which is in the z direction. That's why we have taken as a z square. Otherwise, the entire expression will be related to the cylinder only. Okay. So in this way, the omega, mu, epsilon, these are the constant values in the z direction we can take. These are the constant values means what? If I'm assuming the free space, okay, well and good, that will be my mu 0 and the mu, what we can say, mu 0 and epsilon 0 will be the case. If I'm considering any medium or the material. At that time you need to write here the mu r and the epsilon r value. The omega will be the angular frequency 2 pi f you can take whenever, and these are the constant term. This is the particular in the z direction, and this will be the final k, which is the constant term. This will be related to your the constant in the radius form. So in this way, if you are going to change by rho from the 0 to the a, then definitely the fluxes linking will be the change. In this way you can find the densities at a particular node. Similarly, in the circular waveguides, if what we can say, if you want to plot the graph, or you can do, if you want to observe what is going on of your the sinusoidal waveform, or how the wave will be propagating, so that also you can observe with the help of the current densities. Okay, that is possible by plotting your the at a particular node the current density. If the distance is changing, that is nothing but your the x, that is also possible. Okay, so how it is possible, plot you can plot that graph, and see here you will be able to find, he see here the changes in the peak. So every peak is changing here, likewise changing. So these instant at a particular node, the distance is changing. Okay, the node is changing, because from this point to this point is different, this to this one is different, this to this one is different. So every time the points are changing, that is nothing but the n1, n2, n3, and likewise n number of. Okay, so n number of things, the entire is nothing but the total x, but in the x particular nodes. Okay, so that we are interested along with your the distance. So in this way you can find the current densities in that particular node with by changing the distances. You can plot that one. Okay, and ultimately you can uh, uh, what we can say, observe, and you can find that is your n number of which is not equals to the zero. Obviously number of nodes are not going to be equals to a zero form. So here, what we need to take care here, you can find the current density in the n number of, even the constant parameter with the radius. Okay, and that term is a zero. So in this way here, actually we are interested to find out the k rho, that is nothing but the radius of that constant value. Okay, and how we can find out with the help of the distances, which is changing every time, every node, that is nothing but the np at a particular node. Okay, and with the help of that radius, that is nothing but which is in the form of your the a. Now come to the point here at the beginning, that is you can say the reference point, or the reference point is treated as a zero term. So that is x and 0, that is the value is here at this moment. Here will be the x and 0. Okay, which is will be equals to 0, but it's not necessary to take at that particular moment. So at from the 0 to up reaching up to the any one point, so that will be the consideration instead of taking at the reference point. So see here what they are saying. So here it's not included, obviously it's not included, but at reaching at a particular point you can assume that one. Okay, so in the circular waveguides, every time you can change. Even previously we have seen about the electric field. Here also we can study about the transverse magnetic field, that is nothing but the Dm of a NP mode. Why I am talking about the NP mode? Every time the N will be changed and the P will be changed. What is that P and then the wave propagation P is, and N is the number of nodes. Okay, on a particular direct nodes in the sinusoidal waveform. Why I am writing here my expression in terms of u the z, that is in the cylinder you can say, or the circular in the z direction rotation. If I am talking about the circular, definitely the entire term will be in the cylindrical, and from the top to the bottom, either the top or the bottom, you can assume, and you can cut in vertically, that is nothing but in the z direction. So here the vector, anyhow I need to write that expression in the vector form, then only it is possible. Then only it is possible to simplify that expression. See here how the n is changing every time, because no doubt at all, if this is the sinusoidal waveform, so definitely the nodes are changing every time. That is nothing but the 0, 1, 2, 3 up to the finite. Okay, and here the sinusoidal waveform, so definitely the phi is also varying. Once the phi is varying, how, what will be the node of that at a particular distance, that also you can write here. How I am keeping here, whether my row is 0 or whether my row is again the a is there, then that will be the cancel out, and the exponential form you can write easily. So in this way you can even treat it here. See here, n is a start, see the difference between these two. So n is starting, that is a reference point or the reference node which is 0, but it is not included everywhere, even though that is starting from the 0, but in the expression never used to be a 0 from the 0. Okay, that's why if I am going to be add np directly, so it will be from 0 to 1. See here, my np mode, that is nothing but it is a 0, it is 1, so obviously I will be on the first node, which is not at the reference point, which is not at the 0 point, which is not at the ground point. Okay, at the initial point, in short you can say. So in this way you can write the expression. If this is the root, you can take, no need to write here the 1 by 2, otherwise directly you can take root of k square minus of this np divided by the a of whole square. So in this way we can write all these expressions are required to simplify the numerical while you are going to solve. How I can find the cutoff, because all these things we are starting just to find out the frequencies, just to find out the normal frequency, just to find out the critical or the cutoff frequencies. You just find out the, what we can say, the critical and the cutoff, what we can say, the wavelength and the ground wavelength. Okay, already we have yesterday in the many lectures we have studied, we have simplified the numerical on the basis of your the waveguides. Okay, that is in the rectangular form. Similarly, we were observed how my m is changing, how n is changing, how I am calculating my t, how I am calculating my tm. Okay, how I am calculating my lambda c, how I'm calculating my the lambda g. Okay, like your the fc and the f, all these things is possible, all these things are possible. So before that we must aware from the theoretical part which is related to that particular what we can say, the methods. If I am learning the rectangular, I must aware from my equations, I must aware from the basics, I must aware from the condition which I am going to be applying for simplifying that numerical. Similar to that only, if you want to learn for the circular regards, so definitely I should aware from the application, I should aware from the basic concept, how I can find my cutoff, how I can find my lossy, what we can say, the view, how I can find the tangential view, how I can find, you can say, the propagation of that. Okay, in the circular, in the rectangular, whatever it is. So I must aware from this. Even how I can find my skin depth of penetration, that is a lambda, that is a theta, even the tangential form theta also you need to find out. So all these things are the theoretical background you must aware. Similar to that here, while you are going to find out in the circular the cutoff frequency of your tm in the z direction, so yes, it is possible to find out with the help of that constant parameters, that is a k. Even directly all these three, that is a kz square, k square and the k rho square, you can take directly in the root also. If I am taking my k, total k will be equals to kz square plus k rho square. So directly I can take k is equals to, either you can take the squaring, avoiding the squaring term, or you can take the in the root form. So in short, this will be the total k, this will be the addition of in the z direction, and in the with respect to the, what we can say, the radius, that also possible to find out. But here at this moment I am interested in the z direction, and if initially I am keeping my in the z direction constant value 0, so you can substitute here. So here the effect will be that k and the k rho will be equals to the x and p by a. Now this is the what we can say, scheme depth or depth of penetration. Okay, so lambda is equals to 1 by root of mu epsilon was the case we have studied in the uniform plane wave also. So 2 pi by fc is nothing but the critical frequency root of mu epsilon, and x and p, how we got this one, just because of this expression, how we got this one, just because of this, and how we got this one. Likewise, you can find ultimate finally FCTM, that is nothing but cutoff frequency in the TM mode of a circular waveguide. FC, cutoff frequency or a critical frequency of a TM mode, okay, that too in the circular waveguides. So how we can find this? C divided by 2 pi a root of epsilon r x and p. Here ABC are the dimensions will be there. Many of the cases ABC are the dimensions will be there, or in that particular waveguide if you are going to connect with the capacitor, that also you can take as a C here. but here the diameters are there, dimensions are mentioned here. So that's why we are taking here the APC and the C and divided by 2 pi root r. If value is given, well and good, you can simplify easily. Okay, even velocity of light also you can be treated there. In the quarter frequency of your the TMZ mode, how I can find, see here, how I can find my XNP value, that is important. How I am getting here, that is important. So see here, if at the bottom, if you observe, so these are the X and P values, that is nothing but the P slash N is nothing but 0, 1, 2, 3, 4, you know very well in the sinusoidal I have shown you in the previous slide, starting from the 0, but even though we are not considering, but that will be the 0 point, then the 1, 2, 3 likewise. Here also 1, 2, 3 likewise. See here the N is starting, what we can say, P is starting from 1, 2, 3, 4, N is starting from 0, 1, 2, 3, 4 likewise. Okay, so see here the modes, this is nothing but either you may take is the NP here, okay, 0, 1, you may take here the 1, 1, this 1, 1, you may take here the 2, 1, likewise 0, 2, okay, 0, 2, where is 0? Here is the 0, 2 likewise. Okay, so even in the previous, in the rectangular, we have studied mn. Okay, mn, it may be mn and it may be depending upon that, that is a np. Okay, that is a np. So 0, 1, 1, 1, 2, 1, 0, 2 likewise. So all these things we have already calculated values. Okay, already calculated in the spectrums, you can say, frequency spectrums. So in this way you can simplify easily. If you remember few, that is nothing but 0, 1, 1, 1, 2, 1, 0, 2, a few 2, 2, 3, then directly you can substitute their value in the equation and you can simplify that one without any calculation, without any thing. That is also possible. If you talk about the same, only changing the mode, that is nothing but the electric transverse electric, I mean the Z direction mode, then also it is possible. However, this is the function of your, the f is the one of the function in the z direction. The psi will be again the flux linking and the rho phi z will be the parameters. So psi is the flux linking. How again I can write in the cos. Okay, this cos and the sine is totally depend upon how you are going to be placed in the which particular plane you are placing that your the cylinder. These all these things are in the vectors coordinate system. While you are learning, you are the Cartesian, cylindrical, and the spherical. How we can place our cylinder and in which plane, that is important. Okay, how I can place my spherical in which particular plane, and accordingly you can write that equation. Okay, so here also same similar thing, how I am getting this cos and the sine, how I am getting this np. These are the new, but this cos and the sine totally depend upon the cylinder placing in the particular what we can say, the sheet or the coordinates, you can say. That time you can consider. Why I am taking here the hz, because already we know very well, while we are learning about the te mode, there will be the wave propagation in the magnetic field. Even though